Welcome everyone. Thanks for joining me again. I hope you are all doing well. Today I'm going to show you how to find volume by using integration. So this is one of the applications of integration. We're going to be finding volume of a solid that is obtained by rotating about either the x-axis or the y-axis, or it could be rotated about a line. So before we dive into our example, I just want to give you an illustration on how this is going to work. So pretty much we have a region in 2D, something like this right here, and we want to revolve this around some axis. So say you want to revolve this region about the x-axis. So you're gonna get a plane that is perpendicular to the rotation of axis and run it all the way over to the region, and you start looking at these. So suppose that's the plane, you cut right through it and you create these cross sections. So these cross sections are circular. So the way we're going to be finding the area of this cross section is by using the formula. Area of a circle is pi r squared. So when you add up all of these cross sections and take the integral from here to here, we get the volume. So that's what we have right here. Volume is equal to the integral from a to b of the area function of the cross section. So let's go ahead and take a look at our first example, and I'll show you how to set this up. So here's an example. We're going to compute the volume of this solid, which is obtained by rotating this curve and this curve. That will create a region above x-axis, the y-axis, and the line y equals 2. Let's go ahead and take a look at how the graph looks like. So if I were to draw this in 2D, two dimension, we have y equals x. Well, we know that's just a line right through the origin like that. So I'm just going to draw from here to here. You'll see why. So this is y equals x. And y equals x squared, well, that's just a parabola that looks like this. So the region we're looking at is this part right here. That's why we're going to revolve. So let me go ahead and redraw and just focus on the intersection and the region we're creating. So something like that. This is y equals x squared. So here's the point of intersection. They happen to intersect at 0 right here and at 1. And the y value is also 1. We're going to be revolving this region right here about the x-axis, y-axis, and y equals 2. So let's go ahead and take a look at the x-axis. I'm going to go ahead and show you the solid when you revolve it, so you see what we're doing as we revolve this about the x-axis. So here's the same picture replicated. So if I revolve this about the x-axis, so imagine the picture gets reflected over something like this, and you have this line right here, and as you're revolving, so it's just going around like that, so you're creating these discs that has hole inside. So this is the inner, and that's the outer piece of this disc, which has a hole, so we call it a washer. So when you're setting up the integral, you have the area of the outer shell, outer disc, and the inner disc. So we can set it up this way. Our volume is going to be the integral from a to b. Now these are along the x-axis. You're integrating from here to here. So a and b, a is 0, b is 1. And we're integrating the area function. So since these are disc circles, we can talk about area of a circle. Now we have to be careful because we have a smaller radius and a bigger radius. So we can call them big R for the outer radius of this washer and little r for the inner radius of the washer. So that's what we have right here. This is the little circle, and that's the big circle right up here. So now let's take a look at the 2D picture. How do we figure out this inner radius and outer radius? Pretty much you start from your rotation of axis and draw a perpendicular radius going toward the region, and you go all the way out to the outer function. So that's going to be the big R. Now, what is that distance? Well, that R, it's going to be from 0 all the way to the curve y equals x. So that's just 0 plus x or just x. And the inner radius, well, again, we do the same thing. We start from the rotation of x's, draw a perpendicular line toward the region, stop at the inner curve. That's the little r. So that's going to be from 0 to that curve, which is x squared. So these are my inner radius and outer radius. So my area, it's going to be the area function. It's going to be pi r squared. Now we have to consider the bigger circle, take away the little circle. So we'll consider this to be the pi big R squared minus pi times little r squared. That's how you're going to get just what we want. So what is big R? Well, in terms of x, that's just x. So this is pi x squared minus, and the little r is x squared. This is pi x squared squared. So our area function comes down to pi, and I'll factor out the pi from both of these, x squared minus x to the fourth. So that's what we're going to sub in right in here and integrate. So we're integrating along the x-axis because we have a vertical washer. So volume, it's going to be the integral from 0 to 1. I meant to write 1 here and pi here. X squared minus x to the fourth dx. And the integration is straightforward. Use the power rule of integration. Pull out the pi. You have integral of 0 to 1 of x squared minus x to the fourth dx. So if I integrate this, I have pi times x squared. When you integrate respect to x, you have x cubed over 3. X to the fourth becomes x to the fifth over 5. And we're evaluating from 0 to 1. Plug in the upper limit of integration. We have pi times 1 over 3 minus 1 over 5. And now lower limit of integration, that gives you just 0 minus 0. So this will disappear. And this will just simply be pi times, if I put them in common denominators, I get 5 minus 3. That would be 2 over 15. So we can just say the volume is 2 pi over 15 for this solid. Now we're going to take the same region and revolve about the y-axis. So here's the region. This is the sketch in 2 dimension. And we're revolving now about the y-axis. So you can imagine your washers are horizontal. So here's the 3D image in case you want to see how that looks like. So I'm going to try to do that. Here you go. So I'm revolving about the y-axis now. So my picture will look something like this. So not the best drawing. So let's suppose it looks something like that. And I'm revolving it so we will have washers. We'll have inner loop right here and the outer loop. So we have infinite many of those washers in there. So let's go back to the 2D picture and figure out the inner radius and the outer radius. So like we said earlier, we start from our rotation of axis and we head toward the outer function in the region. So here's my rotation of axis. We head all the way out until we get to the outer function. So that's the big R. And so that's big R. And then the little r is going to be, again, you start from your rotation of axis and we go perpendicular to the inner part of the function. That's little r. So outer radius, it's going to be, so that's going to be this distance right here, which is 0 and then all the way to the curve. So you can say it's just x squared, but because it's horizontal, these washers are horizontal, we have to make everything in terms of y. So if I were to solve y equals x squared in terms of y, you will have a square root of y equals x. And the second equation, y equals x, well, that's x equals y. So my outer radius will be 0 all the way to the function. That will be a square root of y. And my little inner radius is going to be 0 all the way to the function y equals x. That's just x equals y. So these are my inner and outer radius. Now we set up the volume. That's going to be the integral. Now here we're also integrating along the y-axis. So from here all the way to here. So that would be 0 to 1. Pi times the big R square minus the little r square respect to y. Now replace x and y, big R and little r in terms of y. So our volume now becomes the integral from 0 to 1 pi times a square root of y squared, that's big R, the outer radius, and little r, the inner radius, y squared, dy. And now the integration is pretty straightforward at this point. So let's go ahead and do that quickly. So we're integrating from 0 to 1 pi times square root of y squared, that's just y, minus y squared dy. Then we integrate using the power rule of integration. We have y squared over 2 minus y cubed over 3. And we're going to take it from 0 to 1. So this will leave us with pi times 1/2 minus 1/3. And lower limit of integration gives us 0. So this is pi times 1 over 6. So that will be the volume of this solid. For the last part, we're going to be revolving the same region about the line y equals 2. So let's go ahead and take a look at the same image, but now in 3D so that we have an idea of how this looks like. So here's our region, and we're going to revolve about y equals 2. Let's say this is y equals 2. So we're going to revolve around this line right here. So if you revolve it, you're going to imagine something that looks like this. So here's the y equals x, and here's the curve. So let me try to redraw that. This seems not so good. So here's the point, and here's our line, y equals x, and here's the curve. So as you're revolving, you're creating these washers. So there's the inner piece and here's the outer piece. So these are again vertical washers. So we're going to integrate respect to x. So something like that will be the 3D image. Now if I were to do it in 2D, this is how it's going to look like. So I'm revolving around this line right here, y equals 2. So like we said earlier, you start from your rotation of axis, and we're going to go down to our region all the way to the outer function. So right here, that's going to be your big R. And then you start from the rotation of axis, again, go down to the inner function of the region. That's this one, that's little r. So our big R is going to be, so the big R is this distance right here, which varies depending on the function x squared. So since all of this is 2, our big R is going to be 2 minus the height x squared. So that's the big R. And the little r is going to be this distance right here, which touches the curve y equals x. So again, this is 2. It'll be 2 minus that curve. So y r equals 2 minus x. Again, this is along the x-axis, so we're integrating respect to x. So our volume is the integral from 0 to 1, because those are the starting and the end point along the x-axis. Pi times the outer radius squared, so that would be 2 minus x squared squared minus the inner radius, that's 2 minus x squared dx. So vertical washers, we're integrating respect to x. Now let's go ahead and finish integrating. We have pi integrating from 0 to 1, 2 minus x squared. When you expand that, you're going to get 4 minus 4x squared plus x to the 4th. And then when you expand the second part of it and distribute the negative, you'll have minus 4 times plus 4x and then plus minus x squared dx. Hopefully I did the expansion correctly. And now combining like terms and integrating, we get the following from integral from 0 to 1. 4 and 4, we can cancel them out. Negative 4x squared minus x squared, that's negative 5x squared. We have x to the fourth and plus 4x. So these are the term that survives. And now we integrate them. So this is pi times negative 5x cubed over 3 plus x to the fifth over fifth plus 2x squared. And we're going to evaluate it from 0 to 1. So let's plug in the upper limit of the integration. We have negative 5 over 3 plus 1 over 5 plus 2 minus the lower limit of integration gives us 0. And then if we combine all of this into same denominator, you'll have pi times negative 25 plus 3 plus 30 all over 15. And this will give us 8 pi on top over 15. So that will be our volume for this region by revolving about the line y equals 2. All right, so this is it. I hope this helps.